Pacific Northwest, 1890. The forest stretched endlessly. Douglas fir, Sitka spruce, western red cedar. Trees that had stood for centuries, some rising over 300 feet, trunks measuring 15 feet across at the base. A single log could weigh 40,000 pounds. The lumber industry needed them. America's cities were expanding, railroads pushing west, and the demand for timber had become insatiable. But there was a problem no one had solved. How do you move a mountain of wood through terrain where even horses struggled to stand? Men had tried everything. Oxen teams, sometimes 20 animals yoked together, straining against logs that wouldn't budge. Crews working for days to move a single tree half a mile. Logs abandoned in ravines, left to rot because no force on earth seemed capable of dragging them out. The math was brutal. Human muscle and animal power had reached their absolute limit. Then someone built a machine that changed everything. A 30-ton monster of riveted steel and steam pressure that could reach into the densest wilderness and pull logs that weighed more than the machine itself. They said it was reckless. They said it would never work in the mud, the rain, the impossible grades of the Northwest. They were wrong. If you want to see how American engineers turned physics into raw pulling power, hit that like button and subscribe. Drop a comment telling us where you're watching from, because this machine worked everywhere from Washington to the Appalachians, and we want to know if it operated in your region. New historical deep dives every week. Let's get into it. Before the steam donkey, logging was a war of attrition fought with rope, muscle, and desperation. In the old-growth forests of the Pacific Northwest, loggers faced timber unlike anything seen in the East. Douglas firs that had been growing since before Columbus landed. Western red cedars with diameters exceeding 12 feet. Individual logs weighing 15 to 20 tons, sometimes more. Trees so massive that fallers would spend 2 full days cutting through a single trunk with crosscut saws, working in teams, trading off when exhaustion set in. But felling the tree was only the beginning. The real nightmare started when you tried to move it. Oxen were the standard solution. Teams of 8, 10, sometimes 16 animals yoked together in long lines, pulling against logs chained to rough skids made of smaller trees laid perpendicular to the haul route. On flat ground, in dry conditions, a strong team might move a 10-ton log a few hundred feet in an hour. But the Northwest wasn't flat, and it was never dry. The terrain was hostile by design. Steep ravines carved by glacial melt. Slopes angled at 30, 40, even 50 degrees. Ground saturated with rain 6 months out of the year, turning the forest floor into a slick of mud and decaying vegetation. Oxen lost their footing. Chains snapped. Logs rolled backward, crushing anything in their path. Men died. Animals were worked until they collapsed. And the economics made no sense. A logging crew might spend 3 weeks moving a dozen logs to a riverbank or rough rail spur. The rest, sometimes half the timber they felled, was simply abandoned. Too heavy, too remote, too difficult. Millions of board feet left to rot because there was no practical way to extract it. By the 1880s, the math had become unavoidable. American cities needed lumber faster than oxen, and men could deliver it. Fortunes were buried in inaccessible forests, and everyone knew it. The industry needed something radically different, a solution that didn't rely on muscle, didn't tire, didn't slip in the mud. What they needed was a machine that could pull like 100 oxen and operate where nothing else could survive. The breakthrough came in 1881 in the redwood forests of Northern California from a man named John Dalbier. Dalbier wasn't a trained engineer. He was a logging contractor, someone who understood the problem intimately because he'd lost money on it for years. He'd watched his crews struggle with oxen teams that couldn't handle the weight. He'd abandoned timber worth thousands of dollars because there was no economical way to haul it out. And he'd seen the railroad industry solving a similar problem with something loggers hadn't seriously considered: steam power. Dalbier's first machine was crude by later standards, but the concept was revolutionary. He took a vertical boiler, similar to those used in small locomotives, and mounted it on a heavy wooden sled. Connected to the boiler was a simple single-cylinder steam engine that drove a large horizontal drum. Wrapped around that drum was over 1,000 feet of steel cable. The idea was absurdly straightforward. Anchor the machine to a stump or tree, run the cable out to the log, and let steam pressure do the pulling. People thought he'd lost his mind. Steam engines were heavy, delicate, temperamental. They needed constant water, fuel, and maintenance. Taking one into a muddy forest, where it would be exposed to rain, debris, and rough handling by exhausted crews, seemed like an expensive way to create scrap metal. But Dalbier understood something his critics didn't. A steam engine doesn't get tired, doesn't lose its footing, and doesn't care how steep the grade is. It just converts fuel and water into rotational force, hour after hour, as long as you keep feeding it. The first field test silenced the skeptics immediately. Dalbier's machine, weighing roughly 8 tons in its earliest form, pulled logs that would have required 12 oxen. It worked in mud. It worked on slopes. It worked in conditions where animal power simply gave up. Within a year, Dalbier had filed for a patent. Within 5 years, manufacturers like the Washington Iron Works and Willamette Iron and Steel were producing dozens of models, each one larger and more powerful than the last. By 1900, the steam donkey, named for its stubbornness and raw pulling power, had become the standard logging tool across the Pacific Northwest. Machines weighing 20, 30, even 40 tons were being hauled into remote camps, often in pieces and assembled on site. What had seemed reckless in 1881 was now indispensable. The Iron Beast had arrived. Before we go deeper into how this machine worked, make sure you're subscribed. We're covering the engineering secrets behind America's toughest iron beasts every single week. Hit that notification bell so you don't miss the next one. A steam donkey wasn't elegant, but it was brutally effective, and its design revealed a deep understanding of mechanical advantage, thermodynamics, and field practicality. At the core was a vertical fire tube boiler, typically 48 to 60 inches in diameter and 6 to 8 feet tall, riveted from quarter-inch steel plate. Inside, a firebox burned wood or coal, heating water in the surrounding jacket to temperatures around 350 degrees Fahrenheit. The resulting steam built pressure, usually between 150 and 200 psi, which was then routed through a throttle valve to one or more steam cylinders. The cylinders were simple, often single-acting designs with bores ranging from 8 to 14 inches and strokes of 10 to 16 inches. Steam pressure drove a piston connected to a crankshaft, which turned a large-diameter drum mounted horizontally on the machine's frame. The drum, sometimes 4 feet across and capable of holding over 2,000 feet of 1-inch steel cable, was the heart of the pulling system. Here's where mechanical advantage came into play. By running the cable through a series of external blocks and pulleys anchored to trees or stumps, operators could multiply the pulling force dramatically. A machine generating 10 tons of direct pull at the drum could, with a 4:1 pulley setup, exert 40 tons of force on the log. In extreme cases, rigging crews used 6:1 or even 8:1 ratios, allowing a 30-ton steam donkey to move logs weighing 60 tons or more. The cable itself was under immense tension, often 20 to 30 tons of force stretched across hundreds of feet. If it snapped, the recoil could cut a man in half, which is why experienced crews maintained strict danger zones and never stood in the cable's path during a pull. Water was supplied from nearby streams or ponds via a hand-operated pump or a secondary steam-powered pump. Fuel, usually scrap wood from logging operations, was fed continuously into the firebox by a dedicated fireman. The engineer controlled steam flow with a throttle lever and monitored pressure via a simple Borden tube gauge mounted on the boiler. No electronics, no sensors, just pressure, heat, and human judgment. The entire machine was mounted on heavy wooden skids, sometimes reinforced with steel plating, allowing it to be dragged short distances by its own cables or repositioned by a larger machine. When a logging site was exhausted, the donkey was partially disassembled, hauled to the next location, and reassembled in the field, often in less than a day. It was primitive by modern standards, but worked. And in forests where nothing else could operate, that was enough. Operating a steam donkey wasn't just about running a machine. It was a coordinated effort between men who understood that one mistake could kill everyone on the crew. The engineer was the machine's brain. He stood at the controls, one hand on the throttle, eyes moving constantly between the pressure gauge, the drum, and the cable running out into the forest. His job was to feel the load through the tension in the cable and adjust steam flow accordingly. Too little pressure, and the log wouldn't move. Too much, and the cable could snap or the machine could lurch forward against its anchors. Good engineers could sense when a log had snagged on a stump or had dropped into a ravine just by the way the drum responded. Next to him was the fireman, whose only job was to keep the boiler fed and the pressure steady. He shoveled wood or coal into the firebox every few minutes, monitored the water level through sight glasses, and opened bleed valves to release excess pressure when necessary. On a long pole, a fireman might shovel half a ton of fuel in a single shift. The work was hot, relentless, and critical. If the boiler ran dry, it could crack or explode. Out in the forest, the rigging crew did the most dangerous work. These are the men who attached the choker cables to logs, set the blocks and pulleys, and signaled the engineer when everything was ready. Communication was entirely nonverbal, a series of whistle blasts from a steam-powered signal mounted on the donkey. 1 blast meant stop. 2 blasts meant go ahead. 3 meant slack off. The rigging crew had to be in constant visual contact with a signalman, who relayed their instructions to the engineer via whistle code. When the engineer engaged the throttle, the drum began to turn, winding cable at a rate of roughly 200 to 400 feet per minute, depending on the load. The rigging crew watched the cable's angle, the log's movement, and the terrain ahead. If the log hit an obstacle, a stump, a boulder, a depression, the crew had to signal a stop, reposition the cable or blocks, and start again. Logs didn't slide smoothly. They bucked, twisted, and rolled. They knocked down smaller trees. They threw mud and debris. If a choker cable slipped, the log could swing sideways or tumble backward. If a block pulled loose from its anchor tree, the cable could whip through the air with lethal force. And all of this happened in noise that made verbal communication impossible. The hiss of steam, the clank of the drum, the grinding of cable on wood, the crack of breaking branches, every sound was a signal, and experienced crews learned to read them instinctively. There are no safety regulations, no hard hats, no steel-toed boots, no OSHA inspections. Men worked in wool clothing, leather gloves, and cork-soled boots designed to grip wet logs. They improvised repairs with whatever they had on hand: baling wire, spare chain, hammered rivets. Maintenance was done in the field, often while the machine was still running, because downtime meant lost money. The machine was powerful, but without men who understood it, respected it, and coordinated every movement with precision, it was just 30 tons of useless steel. The Pacific Northwest didn't just challenge the machine. It tried to destroy it every single day. Rain was constant from October through April, sometimes 100 inches in a season. The forest floor became a slurry of decomposing vegetation, mud thick enough to swallow a man's boot to the knee. Steam donkeys operated in this continuously, their wooden skids sinking into the ground under their own 30-ton weight, settling at angles that threw off cable alignment and made the drum pull unevenly. Operators compensated by shimming the skids with rocks and split logs, adjusting the machine's position inch by inch until the cable ran true. But rain kept coming, and the ground kept shifting. A donkey that had been level at dawn could be tilted 10 degrees by afternoon, forcing the crew to stop, reposition, and start over. Temperature swings created their own problems. Winter mornings in the Cascades dropped below freezing, turning residual moisture in the boiler's tubes into ice. Firemen had to thaw the system slowly, building small fires and monitoring for cracks in the metal as it expanded. Summer heat, by contrast, pushed boiler pressures higher than normal, requiring constant bleed-offs to prevent overpressure failures. The Borden gauge wasn't precise. It gave rough readings, and engineers learned to judge true pressure by the sound of steam escaping from relief valves and the feel of the throttle lever. Then there were the grades. Logging sites weren't chosen for their accessibility. They were chosen because trees grew there and trees grew on slopes that would be considered extreme even by modern standards. Steam donkeys regularly operated on inclines of 30 to 40 degrees, sometimes more. The machines were anchored to stumps or driven into the ground with steel stakes. But under full load, even a 30-ton donkey could shift, its skids groaning as the cable tried to drag the entire assembly forward. The cable itself was the most dangerous component in the system. Steel wire rope, typically 7/8 inch to 1¼ inches in diameter, made from multiple strands twisted together. Under 20 to 30 tons of tension, it became rigid as a steel bar, stretched taut across hundreds of feet. If a strand began to fray, worn down by friction against rocks, tree bark, or the drum itself, the cable could fail catastrophically. When a cable snapped, it didn't just fall. It recoiled with the stored energy of thousands of pounds of force, whipping back toward the machine or slashing sideways through the air. Period accounts describe cables cutting through trees 6 inches in diameter, severing limbs, decapitating men who were standing too close. Experienced rigging crews marked danger zones with painted stakes and never, under any circumstances, stood within 50 feet of a loaded cable's lateral path. Block failures were equally lethal. The heavy wooden or steel pulleys used to redirect cable were anchored to standing trees, sometimes under forces exceeding the tree's structural limit. If the anchor pulled loose, the block became a projectile, swinging through the forest at lethal speed. Crew members learned to read the sound of wood fibers cracking under stress and to move before the failure became visible. Boilers, though relatively safe compared to locomotive designs, still carried risk. Overpressure incidents were rare but catastrophic. If the firemen allowed water levels to drop too low, exposing the crown sheet, the steel plate at the top of the firebox, to direct flame, the metal could weaken and rupture. The resulting explosion would send superheated steam and boiling water in all directions, scalding anyone within 30 feet. Engineers kept one eye on the water sight glass at all times, and many carried pocket watches to time bleed-offs and water refills with mechanical precision. There are scattered records, company logbooks, county coroner reports, oral histories recorded decades later that mention accidents. A cable failure near Coos Bay in 1903 that killed 2 men. A boiler overpressure event in Grays Harbor in 1911 that injured the firemen and destroyed the machine. But most incidents went unrecorded. Logging was dangerous work, and the steam donkey, for all its power, was just one more variable in an environment that had been killing men long before the machine arrived. The difference was scale. The donkey let crews work faster, pull harder, and reach deeper into terrain that had previously been inaccessible. And faster work, in an unregulated industry, often meant more risk. The steam donkey didn't just improve logging, it redefined what was economically possible. Before the machine, a skilled crew with oxen might move 8 to 10 large logs per day under good conditions, covering distances of a few hundred yards at most. Output was limited by animal stamina, terrain accessibility, and a sheer physical impossibility of moving timber above a certain weight threshold. Logs over 15 tons were often abandoned. Slopes steeper than 20 degrees were considered unworkable. Entire forests remained untouched because the cost of extraction exceeded the value of the lumber. A steam donkey operating with a competent crew could move 50 to 100 logs in the same time frame, pulling loads across distances of a quarter mile or more. The machine didn't tire. It didn't need rest between hauls. As long as fuel and water were available, it kept working hour after hour until the site was cleared or darkness made rigging too dangerous to continue. The economic transformation was immediate and measurable. Logging camps that had been producing 20,000 board feet per week with animal power scaled up to 100,000 or more with steam. Companies that had written off steep-grade timber as inaccessible began recalculating their assets. Forests that had been deemed too remote to log profitably were suddenly viable, and the rush to exploit them accelerated. By 1910, the Pacific Northwest was producing over 7 billion board feet of lumber annually, much of it extracted using steam donkeys and related machinery. Entire towns appeared around logging operations. Forks, Washington; West Fir, Oregon; Quinault, each one dependent on the continuous flow of timber made possible by machines that could work where humans and animals couldn't. The infrastructure ripple effect was equally significant. Steam donkeys enabled the construction of logging railroads, which in turn opened even more remote areas. Narrow-gauge tracks were laid into roadless forests, and the donkeys themselves were used to skid logs to rail spurs, where they were loaded onto flat cars and hauled to coastal mills. The entire supply chain, from felling to milling to export, accelerated in lockstep with the machine's adoption. Ports like Seattle, Tacoma, and Portland expanded to handle the lumber volume. Sawmills upgraded to industrial-scale operations, many of them powered by the same steam technology that drove the donkeys in the field. The economic center of American lumber production shifted permanently westward, and the steam donkey was the mechanical foundation of that shift. Comparisons with modern equipment reveal an interesting paradox. A contemporary logging yarder, diesel-powered, hydraulically controlled, equipped with computerized load monitoring, can certainly pull harder and work faster than a steam donkey. But those machines weigh 50 to 80 tons, require maintained roads for transport, and depend on supply chains for fuel, parts, and specialized technicians. The steam donkey, by contrast, could be disassembled, hauled into roadless wilderness by its own cables, and operated with would scavenge from the logging site itself. It required no external infrastructure, no electricity, no refined petroleum. In terms of mechanical simplicity and field independence, it was arguably more versatile than many of the machines that replaced it. The numbers don't lie. Between 1885 and 1930, steam donkeys were responsible for extracting tens of millions of tons of timber from terrain that would have been economically inaccessible by any other means. They didn't just change logging, they made modern logging possible. By the 1940s, the steam donkey was already becoming obsolete, overtaken by technologies it had helped make economically feasible. The first blow came from internal combustion. Diesel engines offered comparable power in smaller, lighter packages, with fuel that was easier to transport and store than coal or cordwood. Gasoline-powered tractors, introduced in the 1920s, could move logs over rough terrain without the need for cable systems, and as logging roads improved, wheeled vehicles became the more practical choice. The second factor was labor cost. A steam donkey required a minimum crew of 4: engineer, fireman, signalman, and rigging team, plus constant fuel and water supply. A diesel yarder could operate with 2 men and needed only refueling once or twice per shift. In an industry where profit margins were measured in cents per board foot, the economic pressure to modernize was relentless. By 1950, most steam donkeys had been scrapped, sold for salvage, or simply abandoned in the forest where they'd worked. Steel was valuable during and after World War II, and many machines were cut apart and hauled out in pieces. Others were left to rust, their boilers punctured to prevent accidents, their wooden skids rotting into the forest floor. But the steam donkey's influence didn't disappear, it evolved. Modern cable logging systems, still used in steep-slope timber operations across the Pacific Northwest, are direct descendants of the steam donkey's design. The principles remain identical: a stationary engine, a cable drum, a network of blocks and pulleys to multiply pulling force. The power source changed, the controls became more precise, but the fundamental engineering stayed the same. There are places where you can still see the originals. The Collier Memorial State Park in Oregon has several preserved steam donkeys on display, including a massive Washington Ironworks yarder. The Museum of History and Industry in Seattle maintains a working example that's occasionally demonstrated for the public. In British Columbia, the Forest Discovery Center in Duncan operates heritage logging equipment, including functional steam donkeys, as part of its historical programming. And scattered throughout the logged-over forests of Washington, Oregon, and Northern California, you can still find rusted remnants, boiler shells half buried in moss, cable drums overgrown with ferns, skid timbers slowly decaying back into the soil. They're reminders of an era when machines were built to last indefinitely, not because of superior materials, but because simplicity and robustness were the only design options available. What the steam donkey proved, more than anything else, was that you don't need complexity to solve hard problems. You need a clear understanding of the physics involved, a willingness to build heavy enough to handle the load, and the discipline to maintain what you've built. Modern logging equipment is faster, safer, and more efficient in controlled conditions. But it's also dependent on supply chains, electronic components, and specialized knowledge that didn't exist in 1890. The steam donkey worked because it had to, and in environments where failure wasn't an option. That kind of engineering, brutal, simple, and unforgiving, often outlasted the technologies that replaced it. The decline of the steam donkey was as inevitable as its rise had been revolutionary. By the mid-1930s, the logging industry had fundamentally changed. The old-growth forests that had seemed inexhaustible were visibly depleted. What remained was either protected in newly established national forests or scattered across terrain that was finally accessible by truck and tractor. The economic incentive that had driven the steam donkey's adoption, moving massive logs from impossible locations, no longer existed at the same scale. Technological succession happened quickly. Diesel yarders appeared in the 1940s, offering variable speed control, easier starting, and lower operating costs. Gasoline-powered chainsaws replaced crosscut saws, reducing felling time from days to hours. Logging trucks with hydraulic loaders eliminated the need for railroads in many areas. The entire workflow streamlined, and the steam donkey, with its multi-man crew and constant fuel demands, became a bottleneck rather than a solution. The last commercial steam donkeys were retired in the early 1960s, mostly from operations in remote British Columbia and southeast Alaska, where road access was still limited. A few machines lingered in specialty roles, historical demonstrations, heritage railways, museum collections, but as working tools, they were finished. What remains today is fragmentary, but significant. Mechanical engineering students still study the steam donkey's use of block and tackle systems as a textbook example of mechanical advantage applied at industrial scale. Forestry programs reference it when teaching cable logging techniques. Historians of American industry point to it as a case study in how a single machine can reshape an entire regional economy. And there's something else, harder to quantify, but worth acknowledging. The steam donkey represents a particular kind of problem-solving that's increasingly rare in modern engineering. It was designed without CAD software, without computer simulations, without material science labs. It was built by people who understood leverage, friction, heat transfer, and structural loading through direct experience, not abstract theory. The machines that replaced it are objectively better in nearly every measurable way. They're safer, more efficient, less labor-intensive, and far less likely to kill the people operating them. But they're also more complex, more dependent on external systems, and less reparable in the field by someone with basic tools and intuition. The steam donkey worked in conditions where nothing else could, using technology that anyone with welding skills and mechanical aptitude could maintain. It pulled logs out of forests that are now second or third growth timber, visible evidence of extraction that happened a century ago. It enabled an industry that built American cities, and it did so with nothing more sophisticated than steam, steel cable, and an uncompromising understanding of physics. The cost was high. Men were injured. Men died. Forests were cleared faster than they could regenerate, and the environmental consequences of that extraction are still visible today. The steam donkey wasn't a miracle. It was a tool, and like all tools, its impact depended on who used it and why. But as a piece of engineering, it was nearly perfect for its purpose. Simple enough to build in a frontier machine shop. Robust enough to survive decades of abuse in the worst conditions imaginable. Powerful enough to move loads that still seem impossible when you read the numbers today. It's gone now, replaced by technologies that do the same work with less risk and greater precision. But the principles that made it work, mechanical advantage, steam pressure, cable tension, field adaptability, those haven't changed. They're still the foundation of industrial engineering, still taught in classrooms, still applied on job sites around the world. The steam donkey proved that you don't need electronics to solve hard problems. You just need to understand the forces involved, build accordingly, and respect the machine's limits. And sometimes, in the right conditions, that's enough. If you found this deep dive into industrial history valuable, subscribe for more. We're covering the machines that build America, one iron beast at a time. Drop a comment with your favorite piece of historical heavy equipment, and we'll consider it for a future video. Thanks for watching. Educational and entertainment disclaimer. The content on American Iron Beasts is produced for educational and entertainment purposes only. While every effort is made to present historically accurate information about machines, terminology, and industrial practices, this channel does not replace academic research or professional technical study. Historical descriptions, measurements, and interpretations may be simplified for storytelling purposes. Viewers are encouraged to consult primary sources, technical manuals, and academic references for deeper or specialized research.